Okay, we're going to start off the day by identifying all asymptotes and wholes of the function that I give you below. So take a minute and see, put it on pause and see if you can factor and identify any asymptotes and wholes that this function might have. So to begin, we're going to factor the top. That is a difference of squares, so x plus 1, x minus 1. Over, factor the bottom, that's going to become, break down the factors of 5 that subtract to 4. So positive 5, negative 1. And now that we have it factored, if you notice, the x minus 1 on top cancels with the x minus 1 on bottom. So when I'm identifying my vertical asymptote, horizontal asymptote, if we have an oblique asymptote, and then a whole, the fact that these canceled means that we have a whole at the value x equals 1. So it would have been a vertical asymptote at 1, but because we were able to cancel out the top with the bottom, it becomes a whole instead of an asymptote. Now, as far as vertical asymptotes go, I still have 1, and that's going to be at x equals negative 5. And then a horizontal asymptote is based on the exponent of the top and the bottom. Now they match, so x squared over x squared reduces to 1. So I have a horizontal asymptote at y equals 1. And I do not have an oblique asymptote. So that takes care of the bell work today. Now we're going to move on, and we're going to move away from equations, and we're going to talk about polynomial and rational inequalities. So here are the steps that are lined out to solve. We have 4 different steps. So the first step is going to be make sure that you move every term to one side so that the other side is 0, set equal to 0. Find the zeros of the polynomial. So this is what we've been doing up until this point with equations. So we're kind of adding in some more steps. Now the third step is going to be, once we find the zeros, we're going to have to make a sign chart using the values found in step 2. And then we select intervals that satisfy the inequality from the sign chart and write the solution. And so we're going to be focusing, the new parts are going to be step 3 and step 4 of what we have already been doing. Okay? And the rational inequality works the same way. It's just that because it's one function over the other, we're actually going to set the numerator equal to 0 and the denominator equal to 0 and solve to find our intervals that we're going to test. So for the first example, notice my first step says move everything to one side. So I have to move this negative 1, I need to move it to the other side. So I'm going to add 1 and take it to the other side, and that gives me 6x squared minus 5x plus 1 is less than 0. Okay, so from here, now it's just a square term, so I can either factor or use quadratic formula and figure out what my zeros are. I'm going to factor just to show you another example of factoring when you have a number in front. So this is how I set up my factoring problem. If that is a 6x squared, it's going to look like this. 6x over 6. Now, multiply the first and the last. So 6 times 1 is 6. You are breaking down the factors of 6 that add to 5. So 3 and 2 add to 5. Both are going to be negative. So then my last step to this factoring is divide out. Here I've got to divide out a total. The bottom tells me a total of 6. So I'm going to divide the left term by 3. So when I do that, that leaves me with 2x minus 1. And then I'm going to divide out the right term by 2. And that will leave me with 3x minus 1. So notice I needed to divide out a total of 6. Well, 3 times 2 makes 6. So we're good. Make sure you put your inequality symbol back. So this is what I have. So if I were to take each of these terms and set them equal to 0 and solve, I get x equals 1/2 for that term and x equals 1/3 for that term. So what I'm going to do now is I've got to set up test intervals. So pretend like we're on a number line. So I'll just draw a number line up here. Okay, and I've got 0 here, 1/2 here, 1/3 right there. And here's 1. So basically what we're trying to do is we're going to try to find test intervals. So take your zeros. So I've got to find a test point somewhere below 1/3, somewhere in between 1/3 and 1/2, and then somewhere above 1/2. Okay, so I'm going to be testing the intervals from negative infinity to 1/3, 1/3 to 1/2, and then 1/2 to infinity. So what I've got to do is I've got to kind of pick a dummy number that I'm going to plug in for each of these intervals. So negative infinity to 1/3, the obvious number that you would want to choose would be 0. Anytime you can use 0, use it because it will help. And then as far as a number between 1/3 and 1/2 goes, if you plug 1/3 into your calculator, that gives you like 0.33 repeating. And if you plug 1/2 into your calculator, that gives you like 0.5. So I need to find a number that is somewhere in between there. Now I'm going to use 2/5 because 2/5 is 0.4. And then from 1/2 on to infinity, I can use the number 1. So these 3 numbers are the numbers that I'm going to test my intervals over. So what that means is I'm going to take them and I'm going to plug them into my function, this function right here. Okay, and I'm going to test and see when I plug those numbers in, does that give me a true statement or a false statement? Okay, so I'm going to 6 times 0 squared minus 5 times 0 plus 1 is less than 0. Okay, so that ultimately that gives me 1 is less than 0. Is that a true or a false statement? That's a false statement. So that means this interval is no good. I have to exclude it. Okay, so now I'm going to move on and I'm going to plug in 2/5. Okay, and you're going to calculate that out. So when you do the math and you plug that into your calculator, you get negative 1/25 is less than 0. Is that a true or a false statement? That's a true statement. So this interval for sure is included in our solution. Now we're going to test 1. So 6 times 1 squared minus 5 times 1 plus 1 is less than 0. So I've got 6 minus 5 plus 1. 2 is less than 0. Is that true or false? False. So when I'm writing my solutions, you want to be really careful and make sure that you are only writing the solutions that work. So for this, my solution are anything between 1/3 and 1/2. And that is the solution. Okay, so moving on to example B. Same thing. We are going to, first you've got to make sure, is everything moved over to set equal to, or set less than 0. And then from there you can factor or use quadratic formula if you are having a hard time factoring. So I'm going to show you how to factor this. X and X. I'm breaking down the factors of 4 that add to 4. So -2 and -2. So if I set that equal to 0, I only have one solution. They both equal 2. So my test intervals are going to be, if you were to put that on a number line, you know, it would be -infinity up to 2, and then from 2 to positive infinity. So these are going to be my testing intervals. I'm going to choose dummy numbers to plug in. So for the left interval, I'm going to choose 0. For the right interval, I'm going to choose 3. So those are the numbers that I'm going to be plugging in. I'm going to be plugging them into this. So let's plug in 0. 0 squared minus 4 times 0 plus 4 is less than 0. So when you work that out, you get 4 is less than 0. Is that a true or false statement? False. So we have to exclude that interval. And then I'm going to test 3 now. 3 squared minus 4 times 3 plus 4 is less than 0. And we get 1 is less than 0, which is also a false statement. So in this case, I have no intervals that work, so therefore you're going to write no solution. Another way you could write no solution is that symbol. Now, example C is really nice because, first off, step 1 is make sure you move everything to the one side, and that is the case here. The second step is that we factor it or find the zeros, and they've actually got it set up in factored form, so that's really nice because we can just go and set each of these equal to 0 and find our test intervals right off the bat. So this one, my test interval is going to be 9. This one, -3. This one, -2. So if I were to plot those along the number line, I would have -infinity to -3 as one interval, -3 to -2 as a second interval, -2 to 9 as a third interval, and 9 to infinity as my fourth interval. So then again, you've got to go through and you've got to pick dummy numbers that represent those intervals and plug them in. So for this one, I'm going to choose -5. For this one, I'm going to choose -2.5. I'm going to choose 0 for that one, and 10 for the last one. So those are the numbers that I'm going to be plugging in. So negative 5 minus 9 times negative 5 plus 3 times negative 5 plus 2 is less than or equal to 0. That gives me negative 84 is less than or equal to 0. Is that a true or a false statement? That's going to be a true statement, so that interval works. Okay, so then the next one, negative 2.5 minus 9 times negative 2.5 plus 3 times negative 2.5 plus 2 is less than or equal to 0. And when I calculate that all out, I get 2.875 is less than or equal to 0. Does that interval work? No, it does not. Okay, so then I'm going to try 0. 0 minus 9 times 0 plus 3 times 0 plus 2 is less than or equal to 0. And here you get negative 54 is less than or equal to 0. And that interval will work. And now I'm going to try 10. 10 minus 9 times 10 plus 3 times 10 plus 2 is less than or equal to 0. And you get 156 is less than or equal to 0. That interval does not work. So again, you'll want to make sure that in your solution you have only the intervals that work. Okay? So in my solution, I'm going to have, it's negative infinity to negative 3, u negative 2 to 9. Now, before we go on, we need to talk about the sign. Because this symbol right here is less than or equal to, that means that I need to change these from to where they're just parentheses to where we include them. So negative infinity to 9 bracket u bracket negative 2 to 9 bracket. So make sure that you are careful on that symbol, okay? This is the first one that we've done where it's included, and so you've got to make sure if this symbol has a equal to sign underneath it that you do a bracket instead of a parenthesis in your solutions. Okay, now we're going to move down to, this is an example of a rational inequality where you have one function over the other. It's still going to work the same way. First step is always move everything to one side. So that means I've got to move this negative 3. I've got to move the 3 over, so I'm going to subtract 3. So if I do that, that gives me this. Now, I'm going to go ahead and find a common denominator so that I can have just one function over the other. My common denominator is going to be x minus 5. So you can do either going around the world like I've taught you, or find a common denominator. Either way, the 2x minus 7 is not going to change because he already has the x minus 5 on the bottom. But that 3 needs the x minus 5. So that's what it's going to look like. So we're just going to clean up the top now. 2x minus 7 minus 3x plus 15 all over x minus 5 is less than or equal to 0. Combine like terms. So I have negative x plus 8 on top, and I have x minus 5 on bottom. Is all less than or equal to 0. Okay, so first let me explain. You're going to set the numerator, or the top, you're going to set equal to 0, because that tells us our zeros. Okay, but our bottom tells us where we have undefined points, and so we also have to set the denominator equal to 0. So that's how you're going to solve these rational functions, is you're going to take the top, set it equal to 0, take the bottom, set it equal to 0, find any possibilities, and then we're going to do our test intervals just like we've done in the other ones. So if I take my top and set it equal to 0, my numerator, I get x equals 8. Okay, that is an actual 0, where it crosses the x-axis. Okay, then I'm going to take the denominator and set it equal to 0. Now, I get x equals 5. X equals 5 is not a 0, but it is an undefined spot. That would actually be where an asymptote would be. I would have a vertical asymptote at 5. But we have to go ahead and include them in the test interval. So, my test intervals are going to be negative infinity to 5, 5 to 8, and then 8 to infinity. So go through and pick dummy numbers. So I am going to pick 0 for the first interval, 6 for the second interval, and 10 for the third interval. Okay, so then you're going to plug them in. Well, which equation do you plug them into? I would choose this one right here. It's where we have cleaned it up and it's less than or equal to 0. Okay, so choose this one and go ahead and start plugging in. So if I plug in 0, I would get 0 plus 8 over 0 minus 5 is less than or equal to 0. So I get negative 8/5 is less than or equal to 0, which is a true statement. So that guy is included. Now I'm going to plug in 6. So negative 6 plus 8 over 6 minus 5 is less than or equal to 0. So on this one, I get 2 is less than or equal to 0, which is a false statement. So I have to exclude that. Last, I'm going to plug in 10. So negative 10 plus 8 over 10 minus 5 is less than or equal to 0. And I get negative 2/5 is less than or equal to 0. That is a true statement. So again, you go through and you pick for your solution the intervals that worked, that gave you true statements. And I have negative infinity to 5, bracket because of the equal to, u, 8 to infinity. Now, why am I not putting brackets on my infinities? You don't have to put a bracket on infinity because we can't really pinpoint that number to include it because it goes on forever and ever. So we always just use a parenthesis when we're talking about infinity. And there's your solution. So we're going to do one more of rational inequality. First step is move everything to one side. So I'm going to move this 4 over, make it negative 4. So 3 over x plus 2 minus 4 is less than or equal to 0. Now, I want to make it a rational function again, so I'm going to find a common denominator and put it as one fraction. So 3 minus 4 times x plus 2 is less than or equal to 0. 3 minus 4x minus 8 over x plus 2 is less than or equal to 0. So my final rational function, when I've simplified it, is negative 4x minus 5 over x plus 2 is less than or equal to 0. That's the one that I'm going to use to plug in. And again, you set your top equal to 0. So when I set my top equal to 0, negative 4x minus 5 equals 0, I get x equals negative 5/4. That's an actual 0 where it's going to cross the x-axis. Okay, and then remember we also have to include any undefined points, so set your bottom equal to 0, and I'm going to use x equals negative 2 as well. So those are my two test intervals. So what I'm going to do is go negative infinity to negative 2, negative 2 to negative 5/4, and then negative 5/4 to infinity. And those are going to be my test intervals. I'm going to use the dummy numbers of negative 3, negative 1.5, okay, so now on to the application problem. We have a projectile is fired straight upward from ground level with an initial velocity of 384 feet per second. During what time period will the height of the projectile exceed 2,000 feet? So first off, let's start by drawing a picture of what this might look like. So here's 0. This is time. This is height. So I'm going to come here and put like, I don't know, 24. And come up here and put 3,000. So we've got a projectile that was fired straight upward and comes back down. Now what it's wanting to know is at 2,000 feet, so let's say that's right here, it wants to know the time frame. So it wants to know all of this, where it was above 2,000 feet. So we're going to have a starting time where it started, and we're going to have a stopping time where it came back down below 2,000 feet. Okay, so just know that's kind of going to be what we're looking for here. Now they go ahead and give you the position equation, so all we've got to do is fill in with what we know. Now, from physics, if you've taken physics, you know V naught is the initial velocity. So right here in our problem where it says initial velocity of 384 feet per second, okay, that is our initial velocity. So I'm going to go ahead and plug that in. Plus 384 t, and then S naught would be our starting time. So it's at 0. Okay, so now what we've got to do is we've got to figure out what we have is we have our equation, but we need to know when does it exceed 2,000 feet. So is that going to be less than or greater than 2,000 feet? It's going to be greater than. So what I'm going to do is I'm going to take my position equation is greater than 2,000 feet. Okay, now we're going to follow the same steps that we would follow solving our polynomial equations. So first thing you're going to do is move everything to one side, which means I've got to move the 2,000 over. So negative 16t squared plus 384t minus 2,000 is greater than 0. Now, from this point, what we can do is we can use quadratic formula and plug into the quadratic formula. I notice I can actually divide everything here by negative 16 and make my number smaller. Now, this is not a necessary step, but I'm going to go ahead and do it. So that would give me t squared minus 24t plus 125. Now, anytime that you divide an inequality by a negative, that's going to flip the sign around. So is less than now 0. So now my numbers are a lot smaller, so it'll be a little bit easier for me to plug into the quadratic formula. So go ahead and plug it in. So negative b, so negative and negative 24 is 24 plus or minus negative 24 squared minus 4 times 1 times 125 all over 2 times 1. Now, when you calculate all of that out and get it down, it says 24 plus or minus the square root of 76 over 2. Now, the square root of 76 will break down to the square root of 4 times the square root of 19. So we can actually take the square root of 4 out. Square root of 4 is 2. So when I'm rewriting this, I can say 24 plus or minus 2 square roots of 19 all over 2. And then you've got your magic triangle, and you can reduce. So that leaves you with 12 plus or minus the square root of 19 is less than 0. So what we're going to do is we're going to plug those into our calculator. So 12 plus square root of 19 gives us 16.35. 12 minus square root of 19 gives us 7.64. So these are my two zeros, okay? So what I know now is that at 7.64 seconds is where the projectile enters exceeding 2,000 feet. And then as it goes, at 16.35 seconds is where the projectile stops being greater than 2,000 feet. Okay, so my solution, you could set up your test intervals like we've been doing and plug it into this. But because I drew my picture, I can kind of see, I know my interval is going to be, my solution is going to be 7.64 to 16.35. In between those two times are where it's going to be greater than 2,000 feet. And that's rational and polynomial functions.